Hello and welcome to Saturday's edition of Cracking the Cryptic, where that little introduction there was for you, Leo, in Brazil. Thank you very much for your email. I hope you're doing well, and we really do appreciate feedback like that, I suppose. Now, what else is going on today? What is this puzzle on the screen? Well, this is a quite ludicrous creation by the looks of things, where it's called Broken Pencil by the Cogito, because indeed in the grid somehow the Cogito has depicted a broken pencil. This is the sort of the chewing end of the pencil, and this is the end you write your answers in with, and there's this great big line across the middle breaking up that pencil into two halves. Now this puzzle has got enormous plaudits. It's been recommended to us dozens of times. No, not dozens, that's an over-egging of the pudding, but probably a dozen times. And it's also introducing a new idea, which is slightly terrifying. I often say we can't have negative numbers in Sudoku. In this puzzle, the Cogito has decided we do have negative numbers. So the concept is negator cells, which count as their negative value. So this one is going to be rather interesting indeed. And I'll read you the rules in just a moment or two. Let me look at my list of things I need to tell you about before we get cracking. Oh yes, it's the first of the month, isn't it? Which means it is Patreon Reward Day over on Patreon. We have our monthly Sudoku Hunt. It should be out by now. It should have come out at 4 o'clock this afternoon. It's called Duality, and it's the work of those fiends that haunt the Discord server, the Sudoku Skunkworks. 14 puzzles in all of which take two sort of classic variant Sudoku rules. You might have an arrows and crop key or something and merge the two together. So it's an absolutely fascinating pack full of really beautiful Sudokus. And the way it's going to work is if you manage to solve the first 4 of the puzzles in the pack, then you will be able to find a secret web page on the internet which will reveal a keyword. Send us that keyword and you'll be in the competition, in with a chance of winning a signed copy of our book, which will in fact be the only signed copy in existence. Mark and I need to somehow arrange to get together to sign the book, but we will sort that out. If, on the other hand, you are a prodigious solver of Sudoku and you manage to solve all 14 of the puzzles, then you will fully deserve the shout out you will get on the channel before the deadline of the 20th of October. So good luck to you all. I've no doubt we'll get some entries in today, and that's just absurd to me, but do have a go and let us know how much you enjoy the puzzles, because we do try and let the constructors know. Now the other thing, actually, that reminds me, we've got going on Patreon. I managed to get it edited yesterday, is we've got Mark and I's collective battle, we pitted both of our wits against vignettes by Zetamath, this puzzle on the screen. Now this puzzle on the screen is quite mental in that it's got 6 6x6 grids and involves the concept of doublers. So you can only imagine how mad the Cogito is, who takes the concept of doublers and says, no, I reject your concept of doublers, I'm going to introduce negators instead. Humbug. So anyway, Mark and I's solve of vignettes is over on Patreon as well, and do enjoy that. Let us know. Do have a go at Zetamath's puzzle first, though, and let us know. I mean, if you have ideas for which puzzle you'd like to see Mark and I attempt next in this series, do let us know that as well. Now, what else can I tell you about? Oh yeah, we're streaming tomorrow night, 10 o'clock UK time. We'd love to have your company. We're still battling through the puzzles in our free app, which you can get. Just search for Cracking the Cryptic on your app provider. And finally, I'm going to say a very happy birthday to Enrique. Enrique, you've turned 33 today, I think, and your wife Nikki let that be known and says that you both enjoy watching the channel, which we're delighted to hear. So I hope you have a day full of copious amounts of chocolate cake. Now, I can resist it no longer. Let us see what the broken pencil has got in store for us. and I will read you the rules. Normal Sudoku rules apply. Digits along a blue line must have an equal sum within each 3x3 box the line passes through. E.g., row 9, column 7, which is that cell, let's colour it in, is equal to, oh, hang on, my phone is buzzing, that's fine, is equal to row 9, column 6, which is that cell, plus row 8, column 5, which is that cell, plus row 9, column 4, which is that cell, so that makes sense. So, because this line passes through exactly two 3x3 boxes, you can see it passes, it's got some cells in box 8, it's got a cell in box 9, we collect up all the cells and we say that this cell, which is its only cell in box 9, must equal the sum of the digits in box 8. So let's do another one of these. Let's look at this one. So the sum of those two digits, whatever that is, must equal the sum of those digits, must equal the sum of those digits. So this is a very, I think this is one of the great constraints in Sudoku that's not been fully exploited yet, equal sum lines. I'm fully intending to do an app of it at some point. But the cogito has taken equal sum lines and adulterated them. Let me explain. He says, however, every row, column and 3x3 box contains exactly one negator cell. The digit in a negator cell acts as the negative of its value for the purposes of any line that passes through it. E.g., a 4 in a negator cell would instead act as -4. The location of these cells must be determined. Digits in negator cells must contain all the digits 1 to 9 once each. Okay, so there's 9 negator cells we've got to find, one in each row, one in each column, one in each box. And when we find the negator cells and we've pinpointed all 9 of them, we will find that there's 1, 1, there's 1, 2, there's 1, 3, all the way through to 1, 9 in those negator cells. So let's just see if we can work out how negator cells work, shall we? On a short line down here. So let's make that a negator cell. We will choose the colour of red for negator cells. So if this was a 3, we are saying this is a -3 for the purposes of this line. So these two have to add up to more than 3, or that's going to be a negative number or 0. So let's put 4 in here and 5 in here. I managed to pick exactly the numbers that don't work, haven't I? I could do it like this, I think. So 4 and 2 is 6, -3 is 3, so I could write 3 there, I think, and that would seem to work. Unless this is itself was a negator. No, that's silly. You can't have a minus number adding up to some positive number. Oh, actually you could. Oh my goodness me. That's a terrifying thought I've just had. What would happen if that was negative? I bet you that turns out to be true. I bet you this is going to be negative. And then there's probably maybe that's negative as well. Well, it would have to be negative because you couldn't repeat the negative in this row. I'm getting carried away here, but it's just such an attractive idea, isn't it? So let's make this -5. And make that... That's got to be big negative now because we're going to have to add some positive numbers to it. So this would be 1. This would be 3. And we'd have -5 is equal to -9 plus 1 plus... This is completely absurd. Right. Anyway, so you can see we're going to get into trouble with this one, I think. Do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And that means we are going to start with... not many of these lines look appetizing to me. Let's think about this one. There's an awful lot of digitage in this box. That 1, 2, 3, 4, 5, 6, 7. Right, okay, I can tell you the somewhat underwhelming fact that there is a negator cell in those 7 digits, and that's because of maths. In fact, it's quite broken. If we consider what's the minimum you could make 5 different digits in a 7 different digits in a Sudoku add up to, well, it's 28, but in fact these can't add up to 28 because the 2 isn't available. So the triangular number for 7, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 is 28. Now, these add up to more than 28 then, if there's no negator cell, because there's no 2 in them. And that would imply that domino has to add to 28 at least, or more than 28. So does this. That's impossible. The maximum these can be is 8 and 9, which is 17. So there must be a negator in here. And I think the negator must be quite big to correct the counts. That's my gut feeling anyway. So if we... what's the minimum of natural digits I could put into 6 cells along this line? So I could have... well, I must have 6 natural digits, and the minimum they could be is 1 plus 3 plus 4 plus 5 plus 6 plus 7, which is 18 plus 8, which is 26. Right. That's perfect, actually, because that means they must actually be that. Because if we think about 26 and we deduct out of it the maximum negator we could possibly have on the line, well, that would be a 9, then we would get 17, positive 17, which is the absolute maximum I can put on these lines. So if I was to increase any of those digits there, any of the natural digits, even by 1, this would have to be 18 or more, and that's impossible. So this line, I'm not going to pencil mark it, Mark would like me to. Well, okay, the way to think about this is to say, what is the digit that is not on this line then? And that digit is 8, and that's really lovely. Because remember, these are an 8-9 pair, because they must add to 17. Well, I've just worked out that's the 8, which means these are 8s, these are 9s, and we're away. There's a negator 9 on this line, which is in one of those 3 cells. And I can do some Sudoku here. Look, I can plonk some 8s down there. I can plonk some 8s down here. And I can... what else can I do? Maybe not much. I can... 8s and 9s in the middle box have to go in those cells, which means they could have to be along the line here, which oh, hang on, right, okay, well there's definitely a negator on this line. Oh, right, yeah, okay, the massive line in the grid is really interesting, actually. Because I've just noticed that that cell is the same as that cell, is the same as that cell, is the same as that cell. Because, or just by the rules, which are that, obviously, this massive line here only visits box 2 in that position. So that cell is the same as the sum of those cells. But this is a problem. Right, so oh, there's all sorts going on here. So the reason I think this is a problem, well, not a problem, but it does mean that we're going to have to introduce a negative number into these 5 cells, because if these were all positive, and I made those 1, 2, 3, and 4, which is the least I could make them, 10 plus 7 is 17. I can't write 17 into that cell. That's just not going to work, even in even in the cogito's crazy mind. That's not allowed. So this... right, so one of these is negative. In fact, that can't be 9, 8, or 7. So the maximum value of this is 6, which feels very low. It's, oh, no. All right, the maximum value of that is actually 5 by the power of Sudoku. Because, in fact, let's... yeah, this line that's dividing the pencil is quite mental. Right, so we've got those 2 digits are the same, but by the same token, those 2 digits are the same. So all those digits are the same digit. And they can't, right, I suddenly worried about whether they could be negators, but they can't be negators because given they're the same total, if any of them was a negator, they'd all be a negator. And there would be far too many negators in the grid, or negators associated with that number. So these are all positive numbers, and there are 4 of those positive numbers looking at the middle box, which means that cell by Sudoku is orange. Does that mean it's not 8 or 9? Yes, it does, because that's not 8 or 9. So that's not 8 or 9. But this digit, this orange digit, it sees 6 in these positions, and it sees 7, 8, and 9 in that position. So it's 1, 2, 3, 4, or 5. So now I'm going to just come back to the maths on this. So imagine that was a 5. If this is a 5, how does this work? Well, one of the digits is negatived. I'm not sure that's really a word. So the maximum negative digit, I could put a -8 on this line, and then the other digits would add up to at least 1, 2, 3, and 7, which is 13, which does actually work. Okay. So that's probably going to be how this plays out. So what I'm thinking is one of these eight pencil marks is negative on the line. Then I put 1, 2, and 3, and 7 into the other cells. That gets me up to 13 minus 8, which would give me 5. But that is, well, it's certainly possible, but I don't know that that's what it must be. I'm getting very confused by trying to work out how the negative numbers work. Because now I'm suddenly thinking, is that negative? Oh, I tell you what I should do. I think what I should do is to try and keep track of the positions of the negative numbers. Because in this box, I know that the negative number is on the line. So those cells have got to not be negative. So I'll make those. What should I use? I might use grey today. Should I use grey or green? I might use grey today for a change. So these are grey digits are not negators. Now, yeah, okay, so in box 3, it's the 9 that's the negator, so those cells are not negators. These can't be negators, because I need those to be maximally positive in order to get them up to the 17 we need. Now, is it the same here? It must be the same maths down here. Yeah, the minimum value of these cells is 1 plus 2 plus 3 plus 4 plus 6. So that's 16. I can't write 16 into those. So there's a negator in one of those, which means these cells get greyed. So I'm very... Yeah, and I concluded, I think it was correct, that the orange cells, certainly the orange cells that are in the single positions here, these 4, are never negative, because if one of them was negative, they'd all be negative. So these are actually grey. But that one, I'm less confident about. I know it's the orange digit. But if it was negative, what would that be saying? It would be saying that 1, 2, those 4 cells. Ah, that doesn't work. That's really peculiar. Okay, this cell I don't think is negative, is what I'm concluding. Because, bear with me on this, because this is complicated. If it's negative, whatever it's, from a mathematical equation standpoint, what we'd be saying is that this digit is equal to the sum of those, well, these 5 digits, but with this being negative. In other words, we could move this digit across to the other side of the equation, and we could say that double the value of orange is equal to the sum of those 4 cells. Well, the maximum value we know that orange can take now is 5, because we've worked out orange cannot be 9, 8, 7 or 6, which means the absolute maximum value of double orange is 10. But these 4 cells cannot add up to 10, because one of them, at least, has to be an 8 or a 9. So I can't put 1, 2, 3, 4 into those 4 cells. It's impossible. So that, I think all we're getting from that is that this cell is natural, so it gets grade, which is not really a very profound deduction, is it? But that means, okay, that means, well, now I'm thinking about how the rest of this line works, because again, if we could look at this from a mathematical perspective now, we're saying this digit, whatever it is equal to the sum of these digits, where this counts as a positive number. So if I move this across to the other side, we just get 0. So now what we're saying is that the sum of those 4 digits is 0, which is weird in a Sudoku world. But that means one of those digits has to be a negative 6, 7, 8 or 9, and it can't be a negative 9 because negative 9 is no longer available. So there is a negative, it's got to be negative 8. There is a negative 8 in one of these 2 cells. And the reason I say that is because the sum of those 4 cells is 0, if the digit that's negative was not 8, what would it be? And the problem is I'd have to put a natural 8 or 9 on this line. And obviously that's going to contribute to a sum. Even if I add 1 and 2 to an 8 or a 9, I'm going to get at least 11, which I cannot write as the negative number into the puzzle. That doesn't work. So I need perhaps the easier way to think about it, if we think about those 4 digits together, I could do something like 6 negative equals 1 plus 2 plus 3. But that doesn't work here, because I know there's an 8 or a 9 on the line, so we can just instantly dismiss that. We can instantly dismiss 7 equals 1 plus 2 plus 4, because there's an 8 or a 9 on the line. Now, because the 9 cannot be negative, because the 9's negative in this box, it must be therefore the 8 that's negative, so that's not 8. And therefore this line is made up of a negative 8 and 3 digits that add up to 8, so 1, 2, 5 or 1, 3, 4, and therefore there is no 9 on the line. This is just so clever. This is absolutely brilliant. It's so original. Right, and now... Right, well, yeah, now there's loads going on again, because now this is natural because it's a 9, and whenever we get a 9 anywhere in the grid that's not in this box, we know it's a natural 9, not a negator 9. But now 9 is in one of those 3 cells, and 9 can't be here, because if 9 was there, we'd be saying that 9 is equal to 9 plus that digit. And the only thing that I could put in there was 0, and not even in the cogito's crazy brain is that able to be 0 in this puzzle at least, so that's not 9. Actually, that's Bilbo Bobbins, I think, is striking there. Don't know what to do with that. Right, okay, so let's have a look instead at... Can I put 9 here? That would be a natural... No. That doesn't work for another mad reason, which is if this is a natural 9, How do those... Well, then we've got 9 is equal to 9 plus those digits. So the sum of those digits has to be 0. And that's possible with negators, but only if these are the same number. So if this was 3 and minus 3, it would work. But obviously there would then be 2 3s in column 4, so that doesn't work, actually. So these are 9s down here. Now, can you put 9 on this line? If you put 9 on this line, it's a natural 9. Oh, I see, but then that could be a big digit as well. In fact, that could itself be 9. No, that couldn't itself be 9. Because then you'd have 9, then you'd have the same problem. Those two would have to sum to 0. So let's make that 7. If this is 7 and this is 9, does it work? They're both natural. So then we're saying one of these is a negator, and the negator needs to be 2 greater than the other natural digit. So it could be something like 6 and 4. Right, okay, so that is possible. I don't think I can get rid of the 9 from here, however much I might feel it's necessary. Ah, but one of these is a negative... Right, hang on. Well, one of these is -8, so all of those cells get turned grey. So this column... this column, it's only got 3 positions for its negator left. That row is the same because of the symmetry around this strange line coming down the middle. We're getting some interesting patterns. Have I actually got a negator? No, I haven't managed to pin down a negator cell yet after 26 minutes. I've got a negator 9 in here, and a negator 8 in here, and that's it. Right, so where do we look now? Maybe we look back. I've not looked at this box, have I? So we're saying that a number that is a 1, 2, 3, 4 or 5. Oh, not 2 actually. Ah, okay, there's another digit I can get rid of from orange, and that's 2. So this orange is now 1, 3, 4 or 5. Can orange really be 1? If orange was 1, we'd get 1, 1, 1, 1. Oh no, orange could be 1 because these are 8. One of these is 8. I need there to be a 1 on this line. So maybe orange is 1. Right, so if orange is 1, we're saying that oh no. Oh, this is beautiful. I didn't spot this at all. It's absolutely beautiful. Oh, that is so clever. Wow. Wow. Okay, right. Look at orange and where it goes in this box. This is sometimes we solve these Sudokus and you just see what the constructor has in mind, and it's so pretty. It's going to work up there. Oh, it is. Let me just think about this for a second, because I might be about to announce what orange is. Let me just think about this. So, is it... I'm not 100% sure, but I'm gonna claim I know what orange is, and I'm going to claim orange is 5. I believe that is true. And you can pause the video if you want to try and I'm telling you it's to do with these cells and these cells separately and how they interact with this box and this box. And for those of you who managed to do it, congratulations. And now I'm going to probably prove it's not 5 and feel the right Charlie, but let's see. So I think the idea here is that orange is in the sum. So whatever this digit is, we know these 5 cells add up to orange, but orange has to be on this side of the equation by Sudoku. It's in one of those cells. So that means that orange effectively cancels out from the equation, and what we're left with is a situation where 4 of the digits in this configuration, once we take the orange, let's imagine this is the orange. So then those 4 digits have to sum to 0. How is that going to work? How is that going to work? And I think the point here is that because 9 can't be a negator, we're looking at an 8, a 7 or a 6 as being the negator. But here we're given a 6. So if we tried to put a negated 8 in one of these 4 cells, then the other 3 cells would have to add up to 8, including a 6. So you'd have to have double 1. That doesn't work. So in fact, you must only have one of the digits 6, 7 and 8 in this sequence, and it is the digit 6 because it's given, which means the other 3 digits are 1, 2 and 3 adding up to 6. And that means, if you think about it, because we've just said that orange is in this box, and I've said that 6 is in this box with 1, 2 and 3, orange is not 1 or 3. So we can take 1 and 3 out of orange. But we're going to go further than this because so this collection of digits, oh, it's not 8. There's no way there's an 8 down here. So 8 gets placed. That's the other thing I'm just noticing. I don't know whether this is orange or not. It might be. But one of these is orange. I know that these are now 1, 2, 3 and orange, which is 4 or 5. Maybe I'll just put 4 or 5 in there. And I'll remember one of these. So it just depends what orange turns out to be. But look, we can run this argument exactly the same in this box. It's so pretty, this. So we know orange is in one of those cells. So again, it's on both sides of the equation. And that means that the 4 digits in this box, or that are on the line that are not orange, have to sum to 0. And one of them is a 7. So it must be 7. It must be minus 7 is equal to 1 plus 2 plus 4. And that takes 4 out of being orange, because we're saying that there's an orange plus a 1, 2, 4 triple in here. And that means that this is 5. So that means all of these have to be 5. I hope everyone out. So that means there's a 5 down here. I hope you all find that as pretty as I do. That is, oh, that's an 8. That to me is just so, it's such a beautiful deduction. And well, of course, we know that's the negator, and here we know that's the negator. So now I can get to do some more colouring. Look, that's, oh, hang on, I've chosen a very bad colour as my negator colour. I'm going to change my negator colour to not... Oh, maybe I could keep it as orange and get rid of oranges for the 5s. Yeah, I don't need... Well, we just have to make the negator digits, I've now got 2 of them, as distinct from grey as we can. Is that red? Or is it something else? Yellow? Yellow. Yellow's lovely. Right, so we're going to have yellow negators. One of these is a negator. One of these... Oh, right. Oh, beautiful. It's beautiful. So now the 6 and the 7 look into this box and mean that these aren't negators. And that's no negator, I'm just noticing, and that's no negator, and that puts 9 in the corner as a negator. So now 9 is down there. 9 is over here. Aha! And that means I'm going to write 9 there, I think. So what I'm noticing here is I've got dominoes of 9s in boxes 1 and 4, and dominoes of 9s in boxes 8 and 9. And therefore I can ask where the 9 goes in row 7. It's got to be in one of these 3 cells, because it can't be there, and it can't be there by my pencil marking. And Where does the 9 go in column 3? And it can't be there, and it can't be there. So it's in one of these 3 cells. So the only cell that simultaneously is one of those 3 cells and one of those 3 cells is that one. So that's a 9. That's on the pencil. That's a natural 9, because all 9s are natural apart from the naughty yellow one in the corner. So now... Okay, so now we know one of these is a negator now. And we know which one it is. It's that one. Because that can't be a negator. In fact, I need to actually be more diligent about my labelling of negators. None of these are negators, because they would then be a second negator in a row or column. Now, why do I think there's a negator on this line? Well, here the equation is 9 is equal to 9 plus those 3 digits. So the 9s cancel out, and those 3 digits must sum to 0, which means one of them is a negator, and the only one that can be is here. But actually, it's very easy. Well, actually, is it very easy? I was about to say it's very easy to have a digit that's the sum of 2 other digits, but it's not that easy here, because all the high negator digits have gone away. So the maximum this could be is 5. And it can't be lower than 3, because it needs to be the sum of 2 other digits. So that's 3, 4, or 5, which looks like it's potentially interesting in columns 2 and row 8. Okay. I feel like this might be a good time to do some more Sudoku. Can I do more Sudoku here? 8. Can 8 go on that line? 8? No. Okay, so 8 is slightly restricted in box 8. It can't go in those cells, and it can't go here, because it would be a natural 8, and we'd be saying 9 is equal to 8 plus those 2 digits, which can't add up to 1. So I think 8 is in one of those 3 cells. In box 8. Do I know whether well, that's not an... Oh, okay, I know that's not a negator, because I've worked out this is a negator, so I need to do my greyification again, don't I? Let's do that. Oh, actually, the more grey the grid gets, the more difficult it is to see the blue lines, for me at least. Oh, I've got the wrong glasses on. That's why I can't see anything. Good grief. Sorry. Oh. The transition to these glasses, the moment, is strange. Oh dear. Okay. I'm not sure that was a good idea. Okay, come on. That's yellow, so those are grey. So now in this column, it's the same, actually. Look, I think I've just got to be more diligent with my greying. Let's just finish the greying, because I've suddenly noticed in this column I can yellow that, and in this row I can yellow that, which means I can do more grey. So have I got all... No, I haven't quite got all the greys, look. Oh. Oh, that's pretty. Right, okay. That's a 5. That's a 5, because look at the cells that I've got left that are yellow. They all see 5s because of the funny pattern of 5s we've got around the middle of the grid. So where does the yellow 5 go in this puzzle? It goes only there, I think. And therefore those squares add up to 5, which means they are either 1, 4 or 2, 3. And therefore... those are not 5. Those are not 5. So we are very close to having some quadrupleage and tripleage going on in columns 2 and row 8. These squares have got to be from 1, 2, 3 and 4 now. Let me just stare at this for a moment or two. I have a feeling this feels like there's Sudoku to do to me. That could be wrong. I'm often wrong about the nature or the time at which it's appropriate to use Sudoku. Oh, I was about to pencil mark 9s down here, but I've already done it. Can I not know? Do I not know where the 8 goes on this line? That would suggest I see I can get the 8 here if I can get the 8 down here. Which I can. I've already done this. I've already done this logic down here. I can't put 9 here. Because then those are the same number on different sides of the equation. And that would mean those two have to add up to 0. And that means that one's the same as that one, which doesn't work. So these are not 9. That's 9. That's 9. Therefore there is 8 on the line as a natural 8. So that digit's got to be quite big, actually. So let's think about that. If this is natural 8 and then we add the minimum to it, which would be 1, then we've got 9 here minus 4. So this has to be at least 5. It's not 5, it's not 6, it's not 8, and it's not 9. So that's 7. So this is 7, which means I know that digit's 4, which means I know that digit's not 4, so that digit's not 1. Now I've got a natural 8 on one side of the equation and a natural 7 on the other side of the equation. So this negativity needs to be greater by 1 than the naturalness that goes into these cells. So that means that the options for these cells are 1, 2, 3 and 8. I think that's got to be right, hasn't it? Because if I did try and pair up the 8 with a 4 here, for example, that would be 12. I can only minus 3 from that, and that gets me nowhere near. Yeah, so so whatever this is 1 less. The low digit on this line is 1 less than this digit. So this isn't a 1. If that's a 1, that's got to have 0 on it, doesn't it? If that's 1, and that's 8, yes, then this would have to be 0. So this is not 1. This is 2, 3, or 4. Oh, right. I see how we do this. Well, I don't actually see quite how we do it, but I can definitely. This is restricted. This is 3 natural cells that add up to 9, and they can't use 5. So this has to be either 1, 2, 6, which is very difficult for it to be. That would have to be the 6. Hang on, let's do this slowly because this is constrained. Or it's 2, 3, 4. So this would have to be the 4, and there would be a 3 up here. I've got a 1, 2, 3 triple in the row. So that's got to be 7. But what occurs to me here is how could this be a 2? Because if this is a 2, I've got to put 1 on the line, and then the minimum these digits could be would be 3, 4 and 5, which add up to 12, and 12 is not the same as 9. And so that's not right. So this can't be 2. And this is so clever, because once this is down to being 3 or 4, how could that line be 2, 3, 4 now? It can't be. So this is 1, 2, 6. Right, let's do that again. So if it's 1, 2, 6, that's 6. And this is a 1, 2 pair. And that's 3. And we said those two have to add up to that one. So that's 2. This is a 1, 3 pair over here, which means this is a 2, 5 pair. This is not 1 or 2 now. This is not. So this is 3 and 8 apparently, which means that's 4. That does work, okay, because 4 and 3 are obviously 1 apart. So that's a 7 by Sudoku. That's a 1-3 pair, so that's an 8. This is a 3. That's an 8, and we know that 8 is useful because that then is, you've guessed it, yellow. Which means that's yellow. It means that's yellow. And we have fully... That's not 4 because it would repeat as a negator. What a puzzle this is. This, well, I think the Cogito has discovered a new form of Sudoku, frankly. This is absolutely brilliant. 4, 5, 6, 7, 8, 9. Right, these are a 1, 2, 3 triple, and they all have to be different from each other. Right, that digit's just a digit that we can put in the grid. That's a 4. So those are not 4 up there. These digits are 1, 6, and 8 by the power of Sudoku. That's not 8. And what's going on in the middle box? I can't remember what we decided about this. So we've got 5 on both sides of the equation. Oh yeah, so these, right, okay, so these cells have to add up to 0, and one of them's a negative 8, so the others are 1, 3, and 4. Because they can't be 1, 2, and 5 without repeating the 5. So that's not 4. That's not 3. It's very close to being quite profoundly done, isn't it? Okay, so what have I not used here? I've not used this line. This adds up to 9, and it's natural. So this is, it's not 4, 5. If it's 3, 6, it's exactly one way round. If it's 2, 7, it's not 2, 7. There's a 2 and a 7 in the column. It could be 1, 8, perhaps. Only just. So if it's 1, 8, this is 8, and this is 1. And I get another low digit here. I have a feeling we might end up having to colour our low digits. But let's see. Can I double click my 8s for a moment, because I feel like I've got a lot of 8s in the grid. Oh, I see. I'm left with a sort of X-wing of 8s in these cells. This column needs 1, 3, and 4, which is nearly interesting, but not quite interesting enough. I'm scrambling around here. Okay, what? No, I was about to say something that was total and utter. That's a 7 by Sudoku. I hadn't spotted that, so I'll take that with gratitude. That's a 7 by Sudoku, which means that's a 9 by pencil marking. That's a 9 by pencil marking. That's a 7 by Sudoku. So 7s are suddenly coming to our rescue. That's a 7 by Sudoku. I've just got all the 7s out of absolutely nowhere. Have I done all the 9s? Yes. Have I done all the 8s? No, I've got the X-wing of 8s left. I've got very few 6s by the looks of things. So 6, okay. I've got a 1, 3, 4 triple in the middle box, which of course is the natural corollary of having 3 digits that add up to 8. So that is a 2, 6 pair, which means these are a 1, 3 pair, which is that a triple? Not quite. No, it's not quite. Okay, but where does 6 go in this row? It can't go here, so it seems to have to go there. So I just need 1s, 2s, 3s, and 4s in this box. So this is 1, 3, or 4. 1, 2, 3, or 4. So now, oh, I see. So where does 5 go? Oh, yeah. So this being a 5, that seems to mean that has to be a 5 now, which means that has to be a 5. So I've done all the 5s. No, I can get the 5 here though, and that does them all. So this becomes a 2. 2 has to be in one of these cells. It's probably resolved, but I can't see immediately how, and the 2 matches up there. Okay. Okay. So where should we look next? I've got a 1, 2, 3, 4 quadruple in row 2. So I haven't put 6 in this row, so that goes there, which gets me a 1 at the bottom of the grid. So we've now got a 6, 8 pair here. I've got a 6, 8 pair in column 2 out of nowhere, which means that cell has got to be 1, 2, or 4. That feels like it's sort of... This 6, 8 pair doesn't feel by accident, does it? Oh, the 1 here gives me a 3 here, which means that's a 6, because we need to make these add up to 9. Which means that's a 6 and that's an 8, which means that's an 8. Using... This is now only 1 or 2. That gives me a 1, 2 pair in the column and places 3. Not in a corner, but I certainly am not objecting to it. There's a 3 definitely in this domino now, so that's a... Oops, that's not a 3. And I've got a 1, 2, 4 triple in this row. So there's a lot going on. So where do we put... Well, that means that's a 6, I suppose. So that's a 6, that's a 2. This is a 3. That's a 3, this is a 1. So this is not 3 anymore. This column needs 4 and 6. I'm sure that's resolved in some way or other, but I can't see how to do it. And... Okay... Alright, I think this column is going to do it for us, because once we make that 4 by Sudoku, that becomes 4 by Sudoku. This becomes a 1, 3 pair, which seems to give me a 2 here. So this has got to be a 1 or a 6 only, which means that needs to be a 1 or a 6 only. Not 2. Not 2. And we can therefore... 4 and 3 come out of this cell using the power of Sudoku. So I've got a 1, 2, 3 triple here. That becomes 4. That becomes 6. That becomes 4. That becomes 1. That becomes 6. That becomes 1. This becomes a 3, 4 pair. And I've just got to tidy up this. Oh, it's going to be the need for negators to be different, isn't it? So now this being a 2 seems to mean that has to be a 1. Oh, that's lovely. So that becomes a 3, and that does the final patterns. What a finish. Oh, yes. So that's 3, that's 4, that's 1, and that's 4. And I've got a 1, a 2, a 3, a 4, 5, 6, a 7, an 8, and a 9. Oh my goodness me. And they are all in different rows and columns, aren't they? Click tick. Wow. Just wow. What a puzzle that is. Sensational from the Cogito. Novel. And, you know, one of the great compliments that we give Phistomefel puzzles so often is that Phistomefel takes an idea and creates the perfect puzzle first up with it. You know, the first puzzle you see of that genre from Phistomefel is like the best puzzle you can possibly imagine. It's hard to imagine how you could have done much more than that from the Cogito. It's just gorgeous, start to finish. Loved it. Let me know in the comments how you got on. I do enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.